All right, this is 2005, number 2. Circuit showed above resistors 1 and 2, resistance R1 and R2 respectively, and an inductor of inductance connected to a battery of EMF E or epsilon and a switch S. Switch is closed at time t equals 0. Express all algebraic answers in terms of the given quantities and fundamental constants. All right, cool. So determine the current through resistor 1 immediately after the switch is closed. So what is the current in resistor 1 right after we close the switch? Kind of the key to this part right here is knowing that inductors oppose changing current. So initially, switch open, no current in the whole circuit. Immediately after we flip the switch on, inductor is going to keep 0 current in this part of the circuit. It wants to stay the same. So no current is going to pass into this section L right here. It's essentially like a broken wire, right? It doesn't exist. This part is not affected at all or affecting at all the current. So we really just have this single loop right here between the battery R1 and R2, right? We have a simple series circuit where we have R1 and R2 connected in series to a battery epsilon. So we want to determine the current through resistor 1, right? Well, okay, so we can find the total equivalent resistance, REQ. I was doing these in red. For a parallel circuit is just going to be R1 plus R2, right? So we have our equivalent resistance. Then we can go to the total voltage, which is epsilon naught, and we can use our V equals IR equation, where I is going to be the current through the whole thing. It's all one circuit, so it's the same current everywhere, times the equivalent resistance, epsilon equals I times R1 plus R2. And then we're solving for the current, so we divide over to the other side, and we get the current is equal to epsilon over R1 plus R2. Immediately after the switch is closed, current through this whole thing, right? Not just through R1, but also through R2 and the battery. The current through this whole circle, this whole loop, is epsilon over R1 plus R2. Okay, there's part 1. Determine the magnitude of the initial rate of change in the inductor. Excuse me. Rate of change of the current in the inductor. So the equation that we have that we're given in our advanced placement physics C equations is that the potential in the inductor is equal to the inductance, or negative the inductance, times di dt. So if we can figure out, excuse me, the potential here, right, we can just divide L over to the other side and figure out what we need. The hard part about that is figuring out what the potential is going to be. Well, the potential is going to be the same, because these two are in parallel, as the potential over R2. So the potential over R2 is going to be equal to the potential over the inductor. And the potential over the inductor, right, these are the same. So if I can figure out the potential over R2, which is equal to I times R2, that'll be equal to negative L di dt. And we just solve for the current, right? We know the current through this resistor because we solved for it right here. Immediately after, which is the initial rate of change, right? Immediately after, we know the current is, oh, school's over, epsilon over R1 plus R2 times R2 equals negative L di dt. And then we divide the L over to the other side, and we get di dt is going to be equal to negative R2 L. Oh, L shouldn't go on top. R2 epsilon over L times R1 plus R2. There is the initial rate of change of the current. That'll obviously change as the potentials change, but that's the initial rate of change. Determine the current through the battery a long time after the switch has been closed. So a long time after the switch has been closed, we also need to know what happens to inductors after a while, right? What does this inductor end up doing after the switch has been closed for a long time? Well, we know initially it's going to oppose change, but after it stops opposing the change, right? After the current stops changing and just remains constant, inductors act as just plain wires. So we get this situation where this inductor just becomes a plain wire. Well, what happens when this inductor is just a plain wire? We essentially skip R2, right? Because the current gets to this point and has a choice between going through this resistor or going through a plain wire, and 100% of the time, the current's just going to choose the plain wire. And we essentially cut out R2 like it doesn't exist. So after a long time, the current through the battery is going to be like we have a single resistor circuit. So we'll get V equals I times R, right? We can start with Ohm's law. Potential difference is epsilon equals I times R1. We divide R1 over and we get the current is equal to epsilon divided by R1. There's the current through the battery after a long time. It's just a simple one resistor circuit because that inductor goes to a battery. On the axes below, sketch a graph of the current through the battery as a function of time. So we actually know two things about the current through the battery. We solved for two. We know the initial current through the battery, E epsilon over R1 plus R2, and we know the final current of the battery, epsilon over R1, right? Both of those are measured as currents through the battery, right? Because this one was talking about R1. Resistor R1 is connected directly to the battery. They're in series, so they have to have the same current. And this we found as the current through the battery, which is also the current through R1. But so we have the starting and ending currents through the battery. So down here, we're going to have our starting current, which was epsilon over R1 plus R2. And someplace up here, we'll have our final current, epsilon over R1. And our graph should be, we'll get a little asymptote right here. We should get an asymptote approaching that value. All right, where epsilon over R1 is the final current. Sometime after steady state has been reached, the switch is opened. So now our switch has been opened again. We want to determine the voltage across resistor 2 just after the switch has been opened. So now this changes things a little bit, because now, right, if all of a sudden we close the switch, right, this current that was through L, God, I hate that pops up every time. The current that was through L, which we know is I equals epsilon over R1, right, is going to try and stay, right? And it doesn't have, and since we close this switch or open that switch right there, the current can't go through here anymore, right? It can't go down this path because this path is closed. So it has to go up through R2. So right after we open up the switch, the inductor is going to force a current of epsilon over R1 through resistor R2. So we can actually use that to find the potential difference there, determine the voltage across resistor R2 just after the switch has been opened. Voltage equals I times R. We know that the current is going to be forced to be epsilon over R1. We know resistance is R2. and we should get our potential difference of epsilon R2 over R1. Just after the switch has been opened. Let me check those real quick, see if everything matches up. That's not the answers, that's the questions. We get epsilon over R1 plus R2 for A, beautiful. We get R2 epsilon naught over R1 plus R2L for B. Pretty sure that's what I got. Hold on, gotta go back up here. I got the negative sign. I don't know why the negative sign drops off. They do that to me every once in a while. But I got R2 epsilon over R1 plus R2L. R2 epsilon R1 R2L, good. C, we should get epsilon R1. C, we get epsilon over R1. Graph goes from E epsilon over R1 plus R2 to epsilon over, epsilon over R1 plus R2 to epsilon over R1. Good. And last but not least, current, we should get epsilon naught R2 over R1, and we got epsilon naught R2 over R1. Good. It doesn't ask us to put units, I don't think so. We'll be okay there. All right, excellent. There we go. That is problem number 2.